Hello, good day. Okay, so we will proceed with your module 3. Okay, we will be discussing about the Portland cement concrete. Okay, Portland cement concrete mix because in this kind of cement we will be using, in this kind of concrete mix we will be discussing or we will be dealing with the cement paste or with what we call as the Portland cement paste. Okay, as our binder in our concrete mix. So fresh concrete. Okay, so let's try to separate the topic of fresh concrete and the hardened concrete. Okay, so let's try to analyze about the properties of fresh concrete and then the properties of hardened concrete separately. So first is your fresh concrete. Okay, so it means that it is still fresh. It is still to be mixed or newly mixed concrete. Okay, so fresh concrete. So the strength of concrete is affected by the degree of its compaction. It is vital, therefore, that the consistency, or what we know as the ability to flow, if you say consistency, that is the ability to flow of the concrete mix. Okay? That the consistency of the mix be such that the concrete can be transported, placed, and finished sufficiently easily and without segregation. So again, so that is consistency, the flow or the ability of the concrete to flow. So again, the strength of the concrete is affected by the degree of compaction. Okay, if you say degree of compaction, how compacted that concrete mix is. Okay, so that will affect the strength. If you say strength, it depends. We will discuss that one later. We have what we call as the compression, the splitting, and we even have the shear strength of the concrete. Okay, and so on with the consistency. Let's try to discuss later on the next slide what is this consistency. Okay, consistency, what affects your consistency or what affects the flow of your concrete. So we have here what we call as the workability. Okay, so this is almost the same as consistency. However, okay, used to describe the ease with which concrete mixes can be compacted. Okay, completely compacted using the lowest possible WC. If you say WC, that is the water to cement ratio. Okay, so that is the ratio of the water with the amount of the cement used in the concrete. So workability, again, that is the ease with which concrete mix can be compacted. How easily you will compact that concrete mix based on the water and the cement content of that. So of course, you will try to observe an actual concrete mixing. Okay, the more the water on the concrete mix, the easier they are going to mix that one, and then the easier they are going to compact that one. However, that will also be affecting the strength. Okay, the amount of water in it will be affecting also the strength of the concrete mix. Okay, so that's workability. These are the factors that will affect the workability. We have here, just like what I've said a while ago, water content. Okay, adding of water on the concrete mix. So the higher, this arrow going up means the higher the workability, the lower the strength. So again, as I've said a while ago, if you will add more water on it, it is easier for that to be compacted and mixed. So it means that that concrete mix has a big or has a high workability, but the strength will be low. Okay, so that is relationship of workability and strength. Second, that will affect the workability is your maximum size of aggregate. Okay, the lower the surface area to be wetted, the bigger the water in the medium. So again, the size of the aggregate being used, okay, the size of the aggregate being used will affect the amount of water in it. And just like going back to number one, the amount of water in it will affect the workability and strength, or the workability. Let's focus on the workability since that is our focus in this slide. Okay, workability. So again, of course, the bigger the surface area to be wetted, the lower the surface area to be wetted, the bigger the water in the medium. Okay, and then number three, grading of aggregates. Grading of aggregates. Poor grading reduces consistency. If you say consistency, that is again the ability to flow of the concrete mix. So how will that affect your workability? Okay, your grading. poor grading. If we say poor grading, the sizes of the aggregates are concentrated on one size only. That is poor grading. What we discuss on aggregates is that the best grading should be the sizes should be distributed on the different size of the aggregates, isn't it? We have the range of coarse aggregate, we have the range of the size of the fine aggregates. If we say coarse aggregate, the sizes should be distributed, let's say, evenly. That is the best grading. Not just focus on 3/4 inch, not just focus on half inch, okay? Because if that is focused on one, okay, the percentage of grading is focused on one size, then that is poor grading. Okay, there will be a lot. Just imagine the same sizes in all of these sand, or let's say coarse aggregates, the same sizes. What will be the fill of these voids in between the same sizes? Isn't it? There should be a bigger sizes and there should be smaller sizes, so that the smaller sizes will fill the voids of the bigger sizes. So again, that will affect also the consistency, the ability to flow. So it should be a poor grading aggregate being used in your concrete mix. And then again, how is that related to workability, isn't it? So the bigger or the better the grading, the less water it will need for that to be workable. Okay, for that to be easily to be compacted. So the poorer the grading, the more water it will require, so that will be easily compacted and then that will be easily mixed. So again, it will affect your workability. And then for shape and texture of aggregate, okay, we discussed this one on aggregate. The smoother or let's say you are using a rounded shape of coarse aggregate, it is easier for you to mix, or that will be easier to flow compared to using coarse aggregate that is flat, that is angular, because of course that will not be as easy as to be mixed just like your rounded aggregates. So these are the factors affecting your workability: water content, maximum size of aggregate, grading of aggregates, shape and texture of aggregates. By the way, this is about the water content or the moisture content of the aggregates. Oven dry, if you say oven dry, there is no water in it, including the inside of the aggregate. Air dry, if you say air dry, the surface, okay, the surface and some part of the inside of the aggregate is dry, but there is still a moisture inside. Okay, there is less moisture inside. And then saturated surface dry, we call this one the SSD, saturated surface dry. Saturated because all the inside or the internal of this aggregate is moist, but the surface is dry. Okay, there is no water on the surface. And then damp or wet, there will now be water. Okay, you can now see water outside the gravel. So why do we need to consider this? Is that because in considering the amount of water for the concrete mix, you need to consider also the state of the moisture or the moisture content of the aggregate. Because let's say that is oven dry, then the aggregate requires more water because that will be absorbing, or the concrete mix requires more water because the aggregate needs to absorb, okay, or will be absorbing some of the water. Or let's say that is damp or wet, then even if you will just add just enough amount of water, there will be an excess water to be added because of the damp or the wet or the moisture outside the aggregates. So that needs to be considered for the proportioning of your concrete mix. Measurement of workability, okay, how to measure how workable a concrete mix is. We have here your 5 ways, but actually not all of these are commonly used. The commonly used is the first one, slump test, because this is the most convenient and most easiest, or this is the easiest way to measure consistency or workability, I mean, on concrete batching, or if you say concrete mixing on site. Okay, so slump test, compacting factor test, flow table test, baby test, and then Kelly test. So slump test and calibrable test are the common used, okay, on site. But let's say you are on laboratory to prepare or to try to adjust the ratio of the total batch, and you are going just to get a sample on the laboratory to analyze that one, experiment on that, so that you will know what ratio you are going to use on the actual site. Then you can make use of this flow table test. Okay, so this is actually the pictures, but we'll discuss that one by one. So slump test used in detecting variations in the uniformity of a mix given nominal proportions. Okay, so as you can see, we have this this is the this is I forgot this one. This is the form where you will put, where you are going to put the concrete mix. This is the stamping rod. You are going to use that one to compact. Okay, and then after that you are going to, okay, this is upside down, of course. So the bigger diameter is the base, and then the smaller is the upper. Okay, so you're going to fill that one with concrete, stamp that one with given standard number of blows. Okay, per layer you're going to divide that one per layer, and then once that is already full and then compacted, using this handle you are going to raise this one. You're going to raise your casing. Okay, you're going to raise the casing of this, and then of course you will expect that there will be uh, adjustment of that cone shape concrete mix based actually on its mix. If that is of course totally wet, then that will either fall or that will have these are the types of the slump. Okay, so if we say stiff mix, there is zero slump, so that will be perfectly same as the original in case. Okay, even if you will remove the case, then that will never adjust, okay, the shape and the height, because actually if you say slump, what we are measuring here is the different on the original height to the resulting height if you will try to release the concrete mix. So that is the stiff mix, and then we have here what we call as the rich mix. If you say rich mix, this determines that the mix is on its ideal ratio. Okay, so slump varies but satisfactory. It depends. There is a range, but it is satisfactory or it is ideal. Okay, so because of course, if you say stiff, that might be lacking water in it. If we say lean mix, that is too much also. So you should have just enough. That is your rich mix. Okay, so lean mix, you might be having there a shear or collapse slump. If you say collapse slump, that will now totally fall. That will have a very big slump. Okay, that will fall. And then if you say shear type of slump, some part of that will fall, but the other part will be standing. That will happen if we have a lean mix or poor mix. But actually we cannot say that as poor, because there are concrete that needs to be on the lean mix. It depends on the function of this concrete mix. Okay, where are we going to use this concrete mix? But if we have here your rich mix, that should be your true slump. It should be on original shape, and there will be a range of this given slump. So that is the slump test. Okay, using the casing and then the stamping rod, and of course there's a base supposedly, so that will not leak. And of course you need the measuring tape or measuring stick to measure that slump. So compacting factor test. Okay, so this is measurement of the density ratio, actual recorded density to the density of the same concrete that is fully compacted. Okay, so in this compacting factor test, we are trying to get the density ratio of a fully compacted concrete and then the actual recorded density. Okay, so we are using this apparatus. So mostly this is not commonly used on site and on actual site because of the size of the apparatus. But if you have this already, then you can make use of that. So flow table test. So flow table test measures the diameter of the spread after vibration. So self-consolidated concrete, self-compacting concrete. So this is applicable for self-consolidation concrete or self-compacting concrete. And actually this is commonly used on laboratories for experiments or for trial batches, because we need to have this on this what do you call this one, vibration table. You're going to put the concrete mix there. Initially there is a diameter, of course, circular diameter of that, and then you're going to vibrate that one, maybe using vibration table. So of course, as you vibrate, it will now start to collapse further. So the diameter of the circle will increase, and then you are going to measure the diameter initially and final. You are going to compare that one. So that is flow table test. Kelly ball test. So the Kelly ball test, you are using this one. Okay, you have this, we call this one Kelly ball because we actually have a hemisphere. Okay, a hemisphere, half of a ball here, which is a metal, and then this one is we have here on top a vibrator. Okay, so that will vibrate. We are going to put that one on top of a concrete mix, and that will vibrate, and it will penetrate. It will go inside the concrete mix, and then the penetration will be, the depth of the penetration will be measured. Okay, so Kelly ball test. So this might be simple also to apply on site, but of course you need to have something to start your vibration, your vibrator. Okay, so that is Kelly ball test. So those are the indirect way of measuring. Okay, we did not have that baby test, but that is also almost same as your for laboratories. So indirect way of measuring your workability. And then we have here your next important term, segregation. Okay, so that is very important. This is very important term on fresh concrete, because this is actually a primary factor of strength that will affect the strength of the concrete mix. So we have here your, what do you call this one, KCK. Separation of the constituents of a heterogeneous mixture so that the distribution is no longer uniform. Or that means that it is a literal separation of the coarse aggregate with the mix itself. So as you can see here, this is hardened concrete. You can see here your segregation because below it is purely now a coarse aggregate. The fine aggregates and the cement paste is on top. Okay, cement paste and the fine aggregates is on top of the coarse aggregate. And in this fresh concrete steel, you can see there that your coarse aggregate is separated completely. Okay, so that is segregation. So we will discuss here types, okay, or two forms of concrete segregation. Coarse particle tends to separate out since they settle more than the fine aggregates. So again, the coarse aggregate will settle because why is it? Because the coarse aggregate is more dense than the fine aggregates and the cement paste. So how are we going to control this one? Or yes, to prevent this one from happening is that you need to have just enough vibration, isn't it? That for us to compact, you need to apply vibration or manual stamping on the concrete mix in place. But of course, if you have too much vibration, then if you have too much vibration or stamping, then you will now cause the coarse aggregate to settle down because of too much vibration. So vibration is not good also if that is too much. You should have just enough vibration in your concrete mix so that it will not separate. There is no segregation. And one other factor that will cause this type of or form of segregation is that you will try to drop the concrete mix on a higher elevation. Let's say you are going to let's say you are going to pour a very high wall, pure concrete wall. You're going to pour there, and you will try to start pouring on the highest elevation of that. That will drop on a very high elevation. So what tends there again is that the coarse aggregate will tend to go down because of the height that it will be dropped. Because again, your coarse aggregate is dense compared to the other constituents or parts of your concrete mix. Okay, so that's why the others, they are using, if they're using a pump, or you are going to pour it manually, they are using a downspout, or they are using a pipe, or a rubber pipe, or a plastic pipe to carry that one to the location of the supposed concrete mix. Okay, so that they will not drop that one, so that that will not affect, or that will not cause segregation. And then we have here segregation on wet mixes. Okay, separation of water plus cement from the mix. That happens if you have there too much water in it. Okay, if you have too much water on your concrete mix, the water will just carry away the cement paste out from the concrete, or out from the coarse aggregate. Okay, it will now wash away the sand and the cement paste. The water will wash away. So as you can see in the picture, okay, so this is now flowing. The water is flowing away from the mix itself. So what will be left are just the coarse aggregates. Okay, now we have here, this is another important term, bleeding. We know that one as the water gain. Okay, water gain, it means that uh, there will be an excess water based on the supposed ratio of water. Okay, so water from the mix tends to rise to the surface of the freshly placed concrete. Okay, so that is bleeding. Bleeding can be expressed as the total settlement per unit height of concrete. This will happen also if you have too much vibration. Again, due to segregation, the dense material will go down, and the water and the concrete paste will just go on top, or the concrete paste, if it's a concrete paste, that includes the water and the concrete itself. Okay, so that tends to go up, so it means that the water will focus on top, the mixture of water will focus on top. Okay, so that is bleeding. So that's why, in just like in this picture, you will see there, you did not put a water on the top, you just poured that one on the casing or on the form itself, but due to too much vibration, that will the water will just go on top. So what you can see on top of the mix, or on the of the form, is water. Okay, so that is bleeding. Lightance. Okay, so that is actually the effect of this bleeding. Okay, a weak friable layer on the surface of a concrete and sand, cement, excrete, which appears after curing. So again, so that is also now the effect of bleeding. Once you have bleeding on the fresh concrete, once that will harden, you will have what we call as the lightance. Okay, it seems like you have a very clean surface, but actually that is a weak friable layer. It will be easily removed if there is skidding or there is friction on your surface, especially on pavements. That happens on pavements. After curing, that is new, fresh, or newly cured concrete, you're going to use that one. That it seems that that is very good. The texture is very good. But once after some vehicles passes this one, let's say after a month or something like that, there will be now there will now be a change on the surface, because again the surface of that, due to bleeding, is weak already. So due to friction of tires of automobiles, then that will be removed. The weak layer will be removed. So this is the before. It looks good, isn't it? It looks smooth. But after some time, that will looks this way. So there will be now pores, or there will be now voids on top of the surface, or on the surface itself. So again, bleeding will result to this lightance. Okay, so now compaction of concrete. Let's discuss now on how to compact concrete. Okay, so fresh concrete consists essentially of the elimination of entrapped air in the concrete. Okay, it's either by ramming or vibration. So what is the purpose of compaction? Again, is to remove the entrapped air inside the concrete so that there will be no voids. We know this one on actual construction as the honeycomb. Okay, if you try to remove the forms, there are voids inside. Here you can see there are voids on the sides of the member that you casted. Okay, so that is the purpose of compacting. Again, there are ways of compacting. If you have vibrator, all you need to do is attach that one on the forms, and you will of course switch that one on. That will vibrate. Okay, so that will now compact your freshly poured concrete on the member. But if you do not have vibrator, then you are going to do it manually by ramming. It's either you have a rod or other means of ramming, or you are using what do you call this one, hammer. Okay, you are going to ram the forms, the sides of the forms for you to create vibration in it. Okay, so type of vibration: internal vibration, external vibration, and vibrating tables. So again, if you say vibrating tables, that is what I'm saying a while ago, that is commonly used on laboratory, because of course, let's say you are trying to cast a column. You cannot place the column on top of the vibrating table, and then after that is compacted, you will try to place that one on the supposed placement of the column, isn't it? So vibrating tables is commonly used on laboratory. Let's say you're going to experiment on the trial batch. If you say trial batch, that will represent the total, or the batch that will be mixed on the actual site. You are going to get small part of it. You are going to try to experiment on it, and then try to know what should be the ratio for that type of aggregate, for that type of grading. Okay. So again, vibrating tables is for laboratories. Or let's say you are having a precast. Precast, if you say precast, that is casted on location, and you are going to transport that one to be used. But if that is now cast in place, if you say cast in place, that is now actual casting on the site itself. You are going to pour that one on the site itself. Then what we will be using is internal vibration, just like this one. Okay, you have there a vibrate, what to call this one? You are doing the actual vibration on the mix itself. So internal vibration, and then external vibration, that is using a vibrator attached on the forms, or by ramming. Okay, using hammer on the corners or in the sides of this form. Okay, so that is compaction of concrete. Now let's talk about the curing. Okay, so we are still on fresh concrete. It is still not hardened concrete. We are still on fresh concrete, on the process way to hardened concrete. So sample and on-site. So curing of sample, and then curing of on-site. So if you say, by the way, why do we need to have a sample if we already casted that one in place? So again, there are a lot of factors that will affect the strength or the properties of the concrete. Even if you experimented on that on laboratory, that is very different on the actual site. Okay, we cannot actually make the laboratory situation exactly the same as the on-site situation, because there are a lot of factors that will affect that one on site. Okay, so why do we need to have a sample? Okay, get a sample from the actual site, and then that should be tested on laboratory again. If that confirmed with the design. Okay, because if that did not confirm with the design, supposed strength design of your concrete, then you need to apply a measure. Okay, you need to apply a what we call this one. You need to apply methods. Okay, to strengthen your casted concrete on place. That is already, let's say, that is already hardened concrete. What are you going to do? There are methods. Okay, so you need now to, the sample to be tested in laboratory is just for the sake of confirming if it confirms with the design. If not, then there will be methods to be done. Okay, so the question there is, how are we going to cure this concrete? Because you are not just going to lay that concrete, fresh concrete, and then let it behind for that to self-cure itself. Okay, you need to take good care of this. You need to control the environment for that to attain the design, or the design strength that we needed. Okay, so the creation of an environment for a period of time. Okay, it means creation of environment, or controlling the environment for a given period of time, up to the time that fresh concrete will now be totally hardened. If you say totally hardened, it already reached the design strength of it. Because as time goes by, it will be hardened, but it will be cured, but at a certain level. There will be a given range of time that will reach the design strength. If you say design strength, by the way, the strength of that will increase as time goes on, but the rate of that is not continuous. Okay, as it reaches a certain period of time, the increase of strength will now be negligible. So that is what we call as the design strength. Okay, it will reach that one at a certain period of time, and in common concrete, we have that one as 28D. So we have that, we call that one the 28-day strength. Okay, the total curing of this is for that to attain the design strength is 28 days, or that is almost a month. Okay, it depends, but actually that is for the common concrete. Okay, that is for the common concrete. But as you research on your admixtures, there are admixtures, isn't it? There are admixtures that will fasten that will shorten the curing time, so that at just a lower range of time or time period, it will attain the design strength. Okay, that is admixture. We have also an admixture that will try to lengthen the curing time. So not 28 days, it will be more than 28 days because of some purposes. Okay, because of some purposes. And that is your research on concrete and admixtures. Okay, so again, 28 days for common concrete. So what are we going to do here for us to create the perfect environment is you should have the suitable temperature. Okay, not too cold and not too hot. Not too cold because of course the curing will be slowed, and then not too hot because of course the amount of water or the water content, or if you say water content, that is the amount of water on the concrete, isn't it? So because of too hot environment, there will be evaporation. So some of the water in it on the water content will evaporate. Therefore, the water to cement ratio will not be followed because of evaporation. So what we are going to do there is we have these methods. We will discuss that one later on. Okay, so prevention of loss of moisture or providing moisture. Okay, so suitable environment temperatures. Okay, by the way, yes. So I'd rather discuss it here. We have this what we call as the panding. Okay, we say panding after once you will observe that the what we call this one, the cement and water has completely done its chemical reaction, so it will try now to harden a little bit. You can now do this panding. It's either you are going to lay out this what we call this one, impenetrable, or yes, impenetrable surface, or you can say, let's say, membrane. It depends on what is available for that to cover the concrete itself, so that if you are going to put water on top, it will not mix together with the concrete mix. And of course, that's why it should be a little bit hardened, or it will not be as fresh as totally fresh. So they will put there a layer, a membrane, a membrane before they will try to put water in it. That's why panding, because they will now maintain a certain level of water. Why is it? For that to entrap the total mixture below, so that there will be no evaporation. And the reason that they are going to put membrane is that they will not add water on the concrete mix. And then we have here your spraying. Okay, spraying water on the surface of the ongoing curing concrete. So this happens if, of course, you have a very hot weather. So you cannot prevent the loss of water by evaporation. So at a given period of time or an interval of time, you are going to spray water in it for that to replace the water removed due to evaporation. And of course, to control the heat on the pavement itself. And then we have here what we call as the use of membranes. We are going to cover that one by impenetrable, or yes, so impenetrable membrane, so that it will not allow the evaporation of water, so that the water inside the concrete mix will be entrapped inside. Okay, so there are a lot of ways to have this or for this curing, but commonly is that this spray of water, and then panding. Okay, if you have a lot of water, then you can make use of panding. For membrane, you need to have additional cost here because you need to have this sheet to cover, or this membrane to cover the surface, especially if you have a very wide slab that you poured on it, then you need to have a very wide of this layer, so that will be additional cost, but it depends. Okay, so quality of mixing water, this is also important, supposedly, but if you will try to observe on actual construction, if you really cannot provide the suitable water for mixing, then you can make use of the water available, but you need to consider also that the content of the water will affect the strength of the concrete. So suitability of water for mixing in curing process should be considered. Quality of water is covered by saying water must be fit for drinking. So the ideal state of water to be used in mixing and curing should be fit for drinking. If you say fit for drinking, you know the description of fit for drinking. There are no biodegradable materials in it. The acidity should be exact. It should not be as acidic. It should not be totally base. Okay, so that is the ideal. But again, it depends on your location, on actual construction. Okay, I'm talking about actual construction. If you are on the top of the mountain, okay, and along the way of traveling, this water will of course not make it suitable for drinking. It's okay, but you need to consider that the strength will be a little bit affected because of that. Or let's say you are on the sea or on the seashore, trying to cast, let's say, a wall in there, but you cannot of course secure a fit for drinking water, then you can make use of the seawater, but that needs to, maybe you need to have additional admixture to control the salinity of the water from the ocean. Okay, so it depends actually on the methods to be used, but again, the ideal should be water, okay, or fit for drinking water. That should be the ideal type or state of water to be used in concrete mix. Okay, now let's go to pumped concrete. Okay, a type of concrete which is designed to be pump able with relative high slump. So this is now, it depends again, there are a lot of factors that will affect the concrete mix. It depends on the purpose, it depends on the strength, and so on and so forth. So again, pumped concrete, this has a 6 to 8 inch slump, or in okay, times 25, so this will be 150 to 200 slump, should have that slump. Why? Because a pumped concrete needs to be workable and consistent enough. If it's consistent, able to flow, so let's say consistent enough, okay, for that to be pumped, because of course, just imagine concrete mix with less water in it, so it is hard for that to be mixed and then to flow. It is less consistent. Then you're going to pump that one. Of course, the pressure will be exerted by the pump to pump the concrete mix, so that needs to be on high consistency. So if there's high consistency, then that should be having a big slump. Okay, flow, easy to flow. So there are ways. We have this admixture to be added in it, or what you're going to adjust is the water content. Again, so there are a lot of factors that will affect this one. It depends on the design. So that will happen, especially if you will try to, let's say you are going to pump from a transit mixer. You're going to carry that one to a distance, because the transit mixer can only reach this point. it will not reach the actual site of construction. So what you are going to do, you are not going to carry that one, of course, because that will take time, and then the time will affect. You might already, the concrete might already be cured a little bit before it is already hardened a little bit before you will try to put that one in place due to the distance. So what they're going to do is they are using the pump, this pump. Okay, they are going to pump the concrete. So just look at this, or if you say very wide, very massive, just like this one. This is a mat foundation. Okay, say mat foundation, that is a total foundation. It is not separated. It is a very big total foundation on the base of the structure to be erected. So that is very massive. So you really need to make use of pump concrete. Okay, shotcrete. This one is shotcreting. You say shotcrete, you are going to paste this concrete mix on a vertical wall. So that is, or on the edge of a mountain. That is shotcreting. So you really need to have also a concrete which is consistent enough for that to flow, or for that to be pumped on a vertical manner, or on a vertical wall, I mean. Okay, so underwater concreting. So a special technique used to make concreting in water. We call this one the trimming method. Okay, so what they're going to do is they're not going to pour the concrete on the water itself and that will settle down. No, of course, because if you're going to do that, the water that for you pour the concrete mix will be joining or will be adding on the concrete mix. So that will now, of course, that will now change the water to cement ratio. So this is the method of trimming. Okay, so they are going to attach, or they are going to insert inside impenetrable pipe. So it means that you are going to put there a pipe where you are going to carry the concrete from a space, from the environment, inside the water, so that you're not going to mix that one with water. So this is a technique, okay, of trimming method. These are the parts. So driven sheet pile form. So of course you're going to drive the form that will try to encase your fresh concrete so that that will not spread. Okay, and trimming end immersed in concrete. So that should be almost close to your hard stratum, so that water will not go inside, and that will adjust as the concrete goes down. And then of course, so you have here the water, and you have there the pipe, board pipe with watertight quick action joint. So it means that that is waterproof, so that the water will not go inside of this pipe. And then we have this trimmy feed hopper. So this is where you will pour, okay, the concrete from the pump or skip. And then this feed hopper will be hauled by, or will be carried by the crane. So this is the actual of that. This is the pipe going inside. So maybe you are having there an underground water. So you are going to insert there a pipe, and that is where you will attach your feed hopper. That feed hopper will be carried by crane, and then maybe you have there a pump to put the concrete mix on the feed hopper, or you're going to make use of other ways. So this is trimming method, so that you are not just going to drop the concrete mix on top of the water, so that it will not be mixed with the water itself. So hardened concrete. Okay, we are now on your hardened concrete. So that is all about fresh concrete, how to compact fresh concrete, how to attain the just enough slump of that by compacting, and then how to not to call this one, make it flowable, or make it consistent. And then of course there are a lot that we discuss about fresh concrete, how to cure concrete without affecting the desired outcome, and then of course about the constituents of this, okay, segregation, so on and so forth. So that is fresh concrete. So now this is your hardened concrete. So hardened concrete is a product of binding and hardening of the concrete mixture, which contains ingredients quantified in the appropriate proportions. Okay, so binding and hardening, okay, product of binding, or this is what we call as the curing. Okay, And then appropriate proportions of what? These are the constituents. Your binder. If you say binder, that will bind the concrete mix, which is actually the purpose of the cement. And again, there are types of cement, the Portland cement, there are a lot of types of these. The commonly used is the Portland cement and the asphalt. Or bituminous, that is for bituminous concrete. So, binder, or that is the cement. Coarse aggregate, or we know that one as the gravel. Fine aggregate, or we know that one as the sand. And then water, of course. Optional additives, and then the admixtures. Okay, so here comes now the what we call as the additives and admixtures. To differentiate, okay, because some of the students are confused of additives and admixtures. If we say additives, those are already part of the concrete, of the cement. Let's say not concrete, cement itself. That chemical is already in the cement itself. That's why the difference in that content of the cement will try to separate this into types of cement, isn't it? You have the air entraining cement and so on and so forth. Okay, so again, the additives there is the ingredient of the cement itself. Okay, of the cement itself. If you say admixture, that is another ingredient to be added if you are now going to mix the fresh concrete. But the additive is already a part of the cement. The admixture is a separate ingredient to be added on the concrete mix. Okay. And of course, these have the same purpose. It's either that's already added on the cement, or you will be adding it just on the mixing. But there will have the same effect. If that is for air entraining, or if that is for retarding, or if that is for what do you call this one? For a purpose of having or fast-tracking the curing time. Okay, so there are types of these admixtures and additives. Okay, so now that is hardened concrete. So how about this one? Okay, so this is now what we call as the strength of the hardened concrete. So we have what we call as the compressive. Okay, so compressive strength of the concrete is the strength of the hardened concrete measured by the compression test. Okay, compression test. The compression strength of the concrete is measured of the concrete's ability to resist load which tend to compress it. So again, that's why we call it compressive strength. How much load will it carry that is compressing that concrete before that will burst or that will fail? So it is measured by crushing cylindrical concrete specimen in compression testing machine. So these are the samples. These are what we call the samples. Okay, that is in the shape of a cylinder. Okay, you have that in this height and you have that in this diameter. Okay, so that is the standard size of this cylinder to be tested. So that is being cured on site. Okay, once you are going to pour a batch of concrete on the members, you are going to separate a sample for that, and then that will cure together with the member that you poured. Okay, that will cure together. Once it will reach the 28th day, you are going to, or not just 28th day, the others are testing this one before 28th day, and they are going to graph this one. So, but the important there is the 28th day strength, because that is what we call as the design strength of the mix. That is where we will get the design strength. So let's say after 28th day, they are going to transfer that one into a testing laboratory. That they are going to test that one using a machine. We call that one the Universal Testing Machine, UTM. We have that one in the University of the Cordilleras, but for now, due to lockdown, that is not yet available. Okay, supposedly that should be discussed, or that should be an activity on the laboratory, but again, due to this lockdown, we cannot do that. So again, that is compression test. The machine will try to compress this cylinder up to the time it will burst, it will fail, and then the force exerted by that machine is recorded on the computer. Okay, so compressive strength of material. So again, so this is just the typical. Okay, first day, the concrete will attain the 16% of its strength. If we say 16% of its strength, we are talking about the strength on the 28th day, or the fully cured concrete. But actually, as you will look at this, 28-day, you will have this one. That is, let's say this is the design strength. But as time goes on, that will still be becoming stronger and stronger. But now, the range of time compared to the change in the strength is now a very, very small amount. Okay, compared to from 0 day to 28-day. That's why we consider this 28-day as the design strength. Okay, and actually, the rest, the additional strength will serve as your factor of safety for your design. So 28-day, so that will serve as our design strength. So the first day, after 1 day from pouring of this fresh concrete, it will attain 16%. So this is just for typical, okay, but actually it depends on the environment. So after 3 days, it will now attain 40%. Okay, so agad-agad, 7 days, it will be 65%. So others are actually testing samples after 7 days. They're going to record that one. And then 14 days, it will now attain almost. So that is already 90%. And then after 14 more days, so that will be a total of 28 days before it will attain 99 or 100% of its strength. Or 99 again, because as what I've said, that will continue be strengthening as time goes on. But again, that the 28-day is what we will be considering for our design. If you are going to design, if you are on your reinforced concrete already, okay, if you are going to design, you need a a specific strength that you are going to use for your computation, and that is what we are going to use, the 28-day strength of the material or the concrete. Okay, flexural strength. So flexural strength is one measure of the tensile strength of concrete. It is a measure of an unreinforced concrete beam or slab to resist failure in bending. Okay, so this is bending. Okay, they are going to bend sample. So the shape of the sample, by the way, is a rectangular. Okay, on given a certain length. So this is without reinforcement, of course. There is no steel on it. It is a pure concrete that is to be tested. So how are they going to test that one? Unlike in compression, they're just going to compress that one. In here, the rectangular shaped concrete will be placed, okay, will be laid down, and it will be supported on the end. So as you can see here on the figure, there is this support on the base. And then there are two ways to test this one. The load will be applied in here. Half of the load will be applied on 2 points, or the load will be exactly applied. The total load will be applied in the middle. Okay. So this one you are going to apply that one on the 1/3 of the length, and this will be applied on the 1/2 of the length. Okay. So example of this is, okay, pavement, slabs, and beams are examples of elements that are loaded in flexure. Isn't it? Beams that is loaded as a flexural member. And then of course for a wholly-go decompression, that is for the columns. Okay, mostly columns. Okay, those are the example of members that is resisting a compression force. Columns. Okay, tensile strength. How are we going to measure tensile strength? Okay, that is the opposite of compression. But actually, you'll try to compare the compression strength of a concrete with its tensile. The gap is very, very big. Okay, a concrete is known to be very, very strong on compression. Okay, compression way of carrying loads. But for tensile, that is very, very weak. That's why we have what we call as reinforcement. That's why we are trying to add steel in it, because the material that has a high strength on tensile is your metal. That's why you will be having your subject reinforced concrete. It means that we are going to add metal on the concrete for that to be strong on tensile, and of course the same thing with bending. But how are we going to test the tensile? Because we might be needing, okay, your member might be purely concrete only, so you really need to test the tensile of that. So there is no field test or for direct determination of tension under axial loading. Okay, and an indirect method called the splitting tensile test, in which a standard test cylinder is loaded in compression on each side. So the same thing, we have this cylindrical, so just like for the compression, but the way of loading is now on the side. So that is to be crushed, so that the failure will be splitting. That's why we call this one splitting. Okay, splitting test, splitting tensile test. You are going to compress that one and that will split, okay, in half. So that is tensile strength. Okay. Now we have here also what we call as the shear, torsion, and combined stresses. These are also important, especially your shear. Okay, because if you say beam, we have here beam. You are going to load on this part and this is fixed. So the failure there is not just bending. We have what we call as the shear. Okay, isn't it shear? The shear. So we are talking about the strength of the concrete. Let's say this is the member. The strength of the concrete to resist the friction, so that before it will fail. Okay, let's say there's a load in this part and there's no load here. So the failure there will not just be bending, but it could be shear failure. Or torsion. If we say torsion, okay, twisting. Or combined stresses. There will be combination of compression, tension, torsion, shear. Okay, so this is also to be tested on laboratory. Still your UTM, your universal testing machine. Okay, so shear is a loading in which a part of the member attempts to slide or shear along another part. So that is again friction. The ability of this concrete to resist friction. Friction or shear or sliding from each other part. So torsion is, which is a twisting, is also complex and difficult to evaluate. When concrete fails, a combination of stress causes the failure. So again, if a concrete fails, it is not just purely compression. It is not just, there are some which are purely compression. There are some which are purely bending. There are some which is purely shear or purely tensile. But most of the time, the type of stress that will try to destroy a concrete, or that will try to fail the concrete, is a combined of this type of stresses, not just a focused type of stress. Okay. Now let's go to durability. Okay, durability of hardened concrete. Besides its ability to sustain loads, okay, concrete is also required to be durable. Okay, durable. The durability of the concrete can be defined as its resistance to deterioration resulting from external and internal causes. So that is durability, the ability to resist deterioration due to an outside effect or internal effect. If it's an internal effect, that is due to the concrete itself, whatever is there inside the concrete. External, because it depends on its environment. Okay. Deterioration, it will deteriorate. The external cause includes the effects of environment and service condition to which concrete is subjected, such as weathering, chemical action, and wear. Okay, so those are the external factors. Okay, it's either the environment. Let's say the environment is too hot or too cold. That will affect the durability of the member. Or let's say chemical action. Let's say that this side of the concrete or the wall is for the purpose of resisting or of encasing a chemical. So that's why we have again admixtures to be added for a certain purpose of that concrete. So maybe if that is a certain type of chemical, we need to add something for that to be chemical proof in this type of chemical. So again, so those are another factors externally. And then we have here wear. If we say wear, that is using this concrete. The durability also depends on the use of this concrete or the member itself. If that is, let's say we are talking about pavement, it depends on the amount of vehicle passing through it every day. Okay, or the size of the vehicle passing through it. So that is durability. External factors affecting durability. Now, the internal causes are the effects of interaction between the constituent materials, such as alkali aggregate reaction, volume changes, absorption, and permeability. Okay, so alkali aggregate reaction. Alkali aggregate reaction. So that depends on the type of the aggregate, because there are aggregate that contains a certain minerals that will cause the deterioration internally. Okay, that will cause uh, the loss of strength of the material as time goes by. That depends on the type of mineral, okay, being used on your aggregate. So volume changes, and of course, if you say alkali, we call it reaction because maybe there is no effect of that mineral. But once that is mixed with concrete, there will be now a reaction that will take place, and that will affect your durability internally. And then volume changes. Okay, this is important. Volume changes. As we know that a material will expand on a high temperature and will shrink on a low temperature, isn't it? We know that one on chemistry. Expansion and shrinkage of a certain type of material. Even a concrete will undergo expansion and shrinkage, but we cannot see that because that is minimal. But once we will consider a very big, very massive concrete, you can see the difference of shrinkage and so on and so forth. And let's say you will have a sudden change from low to high, that will cause from low to high and high to low, okay, again and again change of this weather or temperature, that will cause what we call as the temperature cracks, or the cracks on the sides. So just like this one, you have here cracks. So maybe that is due to temperature change. Okay, that's why in your reinforced concrete design, we have what we call as the temperature bars. It is not needed to put that bars, reinforcing bars, for the strength. It is not needed for the strength. It is needed to resist the expansion and shrinkage of the concrete from changes in temperature. That's why we call this one temperature bars. So those are the purpose of those. Absorption and permeability. Okay, this is also important internally. Especially if your concrete is air entrained, it means air entrained. There are air as a part of the concrete, or there are voids as a part of the concrete, as a design of this concrete. But once there are a lot of voids, that is now permeable to water. So let's say you use this type of concrete to try to encase a tank. It is an air entrained, which is wrong. Then there will be leakage. Let's say you do not care about the leakage because all you need, what you care is just the water that will be encased. You do not care about the permeability of water, but that will affect the strength or the durability of the concrete that is encasing your tank. Okay, and absorption. That is of course absorption, because as the water will try to penetrate, it will absorb this water. And then permeability. Okay, so those are the factors, external and internal, that affects your durability. Okay, so external causes. Okay, so leaching out of cement. Okay, leaching out of cement. So these are the failures. These are the failures externally of your what do you call this one, hardened concrete. So leaching out of cement. So as you can see, we have this cement-like or salt-like outside the cement that is leaching out of cement. Okay, and then action. This is due to excess of water on the concrete mix. Okay, the concrete will not take this more water in it, so it will actually just leach out, and it will be carrying the cement paste. Action of sulfate, seawater, and natural slightly acidic water. Okay, so look at this. So the content of the water affects the concrete itself, the hardened concrete. So look at that, it is now corroded because of this water. Okay, because of the water on the surface of the concrete. Occurrence of extreme temperature, abrasion, and electrostatic action. Okay, so temperature and abrasion. Abrasion is friction. and then electrostatic action, and then of course the temperature. So this is also another weathering water mass in concrete. Weathering because of the the type of material attached to it. Okay, weathering. Internal causes. Okay, so again this is just the extension of your durability. Alkali. Okay, so these are the effects. Alkali aggregate reaction. Alkali aggregate reaction. So this is an example of that. So it will actually cause breakage or breakage or cracking on your member. Volume change due to difference in thermal properties of the aggregate and cement paste. Okay. So let's say the thermal property of aggregate and cement paste. So the aggregate and the cement is a different material. So you will expect that the cement and the aggregate has different rate of expansion and shrinkage based on the temperature. So let's say that the aggregate has less expansion due to heat, but the cement has a high expansion due to heat. So that means that there will be a difference. The other one is expanding, but the other one is not. Or shrinkage. Let's say that it is very cold. This aggregate has a less effect or a less reaction on or a less action on the freezing, but the concrete will easily freeze or shrink because of freezing. Then of course that will remain, the aggregate will remain the same, but the concrete will shrink. So now the surface or the surface of the aggregate and the cement will create a gap. So that will now create these crackings on your concrete. Okay, permeability of concrete. So again, permeability due to the voids. So that is those are the internal causes. Okay, shrinkage. This is important. This is what I'm talking about a while ago, but it is now separated here. So shrinkage of concrete is caused by setting of solids and the loss of free water from the plastic concrete, by chemical combination of cement with water, and by drying of concrete. So there are a lot of reasons of shrinkage also. Okay, setting of solids and the loss of free water from the plastic concrete. So that will actually, okay, so the loss of water, because the excess water will make your mix or your concrete bulge. Okay, but once that will be lost, then that will now affect to shrinkage. So there should be no excess water in it, so that at original state up to the final state will be the same. There will be no plastic shrinkage. So we know that one as plastic shrinkage. Okay, the loss of free water by the chemical combination of cement with water. Okay, the cement with the water. So again, the water is the common or is the main factor here. We call that one autogenous shrinkage. So again, combination of cement with water, chemical combination. And then by the drying of concrete. Okay, so that's why again, there should be no sudden change of temperature. If there is a sudden change of temperature while you are on the stage of curing, you should control that one, because that will result to this shrinkage, or you will now end up with these cracks on your members due to shrinkage. So again, that is the reason why we are doing panding, we are doing the spray of water, or we are applying a membrane, so that there will be no sudden change or sudden loss of water. Because if there is a sudden loss of water, then you will have this breakage or your crackings due to shrinkage. So types of concrete defects. Okay, we have here a lot types of concrete defects. Okay, so types of concrete defects, you have these cracks. Cracks are formed in concrete due to many reasons, but when these cracks are very deep, it is unsafe to use that concrete structure. Okay, of course. If the cracks are just minimal, maybe that is on the finishing only, that is okay. But if the crack is very deep, it is already affecting inside, then you need to consider that one. Maybe you need to do retrofitting and so on and so forth, other methods. So various reasons for cracking are improper mix, design, insufficient curing. Okay, again, it is important that we need to take good care of it as it attains its strength. So that is curing. Omission of expansion and contraction joints, use of high slump concrete mix, unsuitable subgrade, etc. So this is also important here. Expansion, omission of expansion and contraction joints. So let's say you are talking about a massive concrete here. Very big amount of concrete and very big amount of concrete. It is important for you to put a gap. If you say a gap, a space between them. It's okay not to, of course, not to give a very big, because that will now neglect the work of the purpose of this concrete, or that will not actually not attain. That is the cause of not attaining the purpose of that concrete. So maybe you are just going to give a small gap for the purpose of the expansion and shrinkage, because maybe because of that gap, even if that will expand, it will not compress each other, because if they are totally okay with each other and they will expand, then that will cause each other to compress each other. So that will now actually apply compression load on each other, so that will cause a breakage or a shrinkage also. Then that will be free to shrink if they are not connected. Okay, so expansion and contraction joints. And then use of high slump concrete mix. Okay, if you say again, use of high slump concrete mix, what is the reason why we have a high slump? Is due to a lot of water. So again, as we discussed on the previous slide about shrinkage, loss of this excess of water will cause shrinkage also. Okay, so, and then of course unsuitable subgrade. Okay, cracks. Maybe your subgrade, if you say subgrade, that is where you will lay your concrete. Your subgrade is weak. That is weak. That is the reason why we are trying to explore the layers of soil before in building construction. We are trying to explore this soil type before we will try to pour the foundation. Because even if you have a well-designed foundation, if your subgrade is weak, then that will affect, or that will cause the failure of your structure. And a lot. Okay, and a lot. So cracks. Crazing. Crazing, also called as pattern cracking or map cracking, is the formation of closely spaced shallow cracks in an even manner. Crazing occurs due to rapid hardening of top surface of concrete due to high temperature, or if the mixed concrete contains excess water or due to insufficient curing. So this is the pattern crack, so we know that one as crazing. Okay, so again, but this is actually not that. This is not that big effect on the member itself, because this is a shallow. That is on the maybe finishing or in just the surface of the concrete. So again, these are the reasons. It's either rapid hardening. So again, it is on the curing itself. Rapid hardening. So there should be no rapid hardening. There should be just enough. Okay. Too high temperature. So again, that is in curing. Excess water content. So that is now on the mixture itself. Water to cement ratio. And then insufficient curing. So not enough curing will lead to pattern cracks or crazing. Blistering. So again, this is now actually just like the lightans a while ago. Okay, so this is the technical term for the lightans. Formation of hollow bumps. Okay, of different sizes of concrete due to entrapped air. So if there is an entrapped air on the layer just before the surface, then that will cause the separation or the removal of the surface or the top surface of your concrete. Okay, so under the finished concrete surface, and it becomes due to excessive vibration. Okay, again, excessive vibration will lead to bleeding and lightans. So after that is cured, and then again there will be, let's say this is a pavement, vehicles passing through it, there will be friction or abrasion, then that will lead to this blistering. Improper finishing. Okay, the mix of the finishing is not that good, so that will also result to blistering. Delamination, this is almost the same as blistering. Okay, in this case also top surface of concrete gets separated from underlying concrete Hardening of top layer of concrete before the hardening of underlying concrete will lead to delamination. It is because the water and air bleeding from underlying concrete are struck between this surface, but hence space will be formed. Okay, so this is caused by the different duration of the curing of the top surface and the underlying concrete, or the concrete inside this top surface. So again, that will happen if there is no proper curing. There is a sudden loss of water on the top, then that will harden, okay, right away compared to the concrete inside it. So if this is already hardened and this is still fresh, then as the underlying concrete will try to cure, the excess water will now rise, and that is already hardened. The top surface is already hardened, therefore the water will separate these two, the underlying concrete and the top, or the finishing. Therefore, that will now be removed once there will be abrasion, friction, and so on and so forth. So delamination. Your blistering is due to bleeding only, okay, interrupt and so on and so forth, or improper finishing. But for this, due to the curing of the top, different stage of curing of the top and the finishing and the underlying concrete. Dusting. Okay, so again, this is for bleeding, because of bleeding. So because of bleeding, again, the excess water and then the cement will go on top. Okay, so that will make a weak band, or that is now the lightance. Actually, the lightance, the removal of that lightance, we call that one the dusting. Okay, so dusting. Curling. Okay, so curling, this is actually not that important on, or not that observed. Not, sorry about the word important. Not that observed, supposedly. This is due to difference of the temperature of the top and the subgrade. If it is very hot on top, okay, if it is very hot on top, then the side of the slab will try to expand, while the other side is still the same. So that will expand, therefore it will curve that way. But, or if the subgrade is now hot and the top of the pavement is cold, then that will bend that way. But actually, this is not that observed, okay, because of course, once you will have a weather of very hot weather, it will actually affect the subgrade. But in other cases, like the subgrade is a different type of material, then this will be very important also. Curling. Efflorescence. Okay, efflorescence is the formation of deposit of salts in the concrete surface. Formed salt generally white in color. It is due to the presence of soluble salts in the water, which is used in making concrete. So this is the problem in using a salty water, or if you are using water from the ocean, of course that is salty water. This is the effect of that efflorescence. Okay, the salt material will actually leach outside and it will go to the surface. Okay, scaling and spalling. So this is almost again separation of the surface, but this is important because, okay, scaling and spalling, in both the cases concrete surface gets deteriorated and flocking of concrete occurs. The main cause of this type of cases is penetration of water through concrete surfaces. This makes the steel gets corroded and then spalling or scaling may occur. Okay, so again, this is due to water. Okay, the type of water being used, and then penetration of water. Okay, so this is just like your blistering and what to call this one, dust delamination. This scaling on top. But for spalling, okay, this spalling is actually due to the reinforcement, or the what to call this one, the reaction of the reinforcement with the water that is passing, or that is entrained, or that is entrained in the concrete itself. So let's say the water, a certain water or an acidic water will penetrate the concrete. It will corrode the metal, and we know that this reinforcement that we are using is prone to corrosion. So you should not. That is the reason why if you are using reinforced concrete, you should not use an acidic water because that will affect to corrosion of your concrete, and then this failure will happen. This is falling. Okay, so that's it. Let's try to separate this method of proportioning so that it will not make our video very long. Okay, so that is for hardened concrete and fresh concrete. We'll separate the proportioning of this.